Lesson 1.3 is function composition. And you can see from the last lesson, we started talking about functions, evaluating functions, domain and range, and piecewise defined functions. And we are continuing our discussion. Function composition is very important throughout mathematics and certainly in calculus. How do we define this? Well, we need two functions, f and g, and then for each x in the domain of G, such that G of X is in the domain of F, we can make this definition, F compose G. But what this is you put in G of X into the function F. You see? We have this G of X here on the inside, and that's where I get this terminology. My inside function, I will typically call G of X, and my outside function I will refer to as f of x. But you can see by looking at this definition, you are evaluating f at g of x, and this is why we need this part, that g of x must be in the domain of f. So let's just do this example, and then we will continue with more. Here we have f of x is x squared plus 3, g of x is x minus 1, and we will calculate f compose g and also g compose f. F compose g of x. This is f of g of x. And g of x is x minus 1. Now, we put this into the function f. Everywhere you see an x in the formula for f of x, we put in x minus 1. So you have x minus 1 squared and then plus 3, except it asks us to simplify. Simplified, well, how do we simplify this? Well, note that this is x minus 1 times x minus 1, and you can do first, outer, inner, last, for example, to multiply all this out. And when we do, you see, we get x squared, we get minus x and minus x, which is minus 2x, and then we have plus 1. So I have this simplified. This is x squared minus 2x plus 4. Now let's compute the other function composition, which is g compose f of x. What this one says is you put in the formula for f of x, which is x squared plus 3, into function g. And g is x minus 1. So everywhere we see an x, we put in x squared plus 3. So you have x squared plus 3 minus 1. We get x squared plus 2. Now you see this note at the bottom. I'm going to make a very important note because you notice these are not equal. This function is x squared minus 2x plus 4, and this function is x squared plus 2. And this is our first important comment, is that g compose f is not equal to f compose g. And this is a general statement. It's important to understand with this first example. Now, let's practice some more. So here I have three functions, f, g, and h. And I'm going to be evaluating some composite functions at different numbers and or explain why it's not defined. Let's get started. Well, here, what we want is f of g of 2. So the first thing I need is g of 2. Maybe I will calculate this first over here. G of 2 is 1 over 5 minus 2. This is 1/3. Now compute f of 1/3. Well, f is 1 over x squared, so this would be 1 over 1/3 squared. Well, we don't really want to leave our answer like this. Typically, we don't want to leave a fraction in the denominator. So when I square this, I get 1 over 1 over 9. Now, how do we simplify this? Well, whenever you have, say, a over b divided by c over d, We can simplify this by inverting and multiplying. So this is equal to, say, A over B times D over C. Okay. Well, in this case, my denominator is 1 over 9. So when I invert and multiply, I am multiplying by 9 over 1. So this is 1 times 9 over 1, which is 9. So this is the answer to letter A. Letter B, here we have F composed H of 6. So this will be F of H of 6. Now, as before, let's come to the side and calculate H of 6. This is the cube root of 6 plus 2, which is the cube root of 8. The cube root of 8 is 2, because 2 cubed is 8. The cube root of 8 is 2. So what I want here is F of 2. And I see the formula, this would be 1 over 2 squared. So this is 1 over 4. And this will be my answer to letter B. Now we have 2 more in this problem. F composed H of negative 2. Well, just as before, the one right above, this would be F of H of negative 2. So we evaluate H of negative 2. This is the cube root of negative 2 plus 2. And this is 0. So what we want here is F of 0. Now, what happens when you try to do this? We run into a problem because this would be 1 over 0. 0 is not in the domain of F. This is one of the things we discussed last lesson. We may not divide by 0. And so this is undefined. As 0 is not in the domain of F. Letter D. Here we have 3 functions. So what does this mean? First, you do h of minus 3, and then g of h of minus 3, and then f of that. So this will be exciting. Maybe I will write that. This is f of g of h of minus 3. Now make sure I close all of my parentheses. So the first thing I need is h of minus 3. This is a cube root, minus 3 plus 2, which is the cube root of negative 1, which is defined. This is negative 1. Well, one more equals, this is f of g of negative 1. So now we put negative 1 into function g. Maybe I will do that below. G of negative 1. This is 1 over 5 minus 1. This is 1 over 5 plus 1, which is 1 over 6. So now we have f of 1 over 6. Well, we're going to have another fraction in our denominator, and we will invert and multiply again. So this is 1 over 6 squared, which is 1 over 36. When we invert and multiply, very similar to letter A, we get 36. This will be my answer here. So that one took a number of steps because we were composing 3 functions. This next type of question, for which we have 3 examples, is a little bit different, but it's fantastic for us to think about. So we are given a function, p of x, in letter A, letter B, and letter C. And what we want to do is find the outside function f and inside function g that makes p this function composition. Now, There are more than one possible answer, just as a comment. So if you are thinking something slightly different than me, it doesn't necessarily mean that it's wrong. And usually how I go about this is I will look for G, this one, first. You want to look for the inside function. For instance, do you see parentheses? Do you see a square root? Do you see something up inside of an exponent or inside of some function, right? That's what we're really looking for here. And so for example, I do see this in letter A. I would take G of X to be, well, I see parentheses, 5x squared plus 6. The question is, how do I find function f? Well, what you want to do is in your mind, you replace this entire inside function with just an x and read off what you have. So if I replace this in my mind with an x and read off what I have that f of x. My outside function is x to the 4/5 power minus 10. And you can check if you wanted, it's not a bad idea as you're working through problems that if you take f compose g, you do in fact get this p. Next one. Once again, I look for an inside function. I see a radical, okay? So I'm going to take what's underneath the radical as my inside function. My g of x is 10x to the 7th power plus 2x cubed plus 5. Now, if you're looking for your outside function in your mind, replace this polynomial with an x and read off what you have. Well, you can kind of see it. It's 3 divided by square root of x. And once again, you can check. If you take f compose g, you in fact get this p. Now, letter C. You see, I see 8x minus 3 and 8x minus 3. I see it twice. And in particular, one of the times, I definitely see the parentheses. So I'm going to take 8x minus 3 as my inside function. My g of x is 8x minus 3. In my mind, I replace this with an x, and I have to do it both places, and then I can read off what I have. You notice this is x to the 9th plus 1 over x. So this will be my outside function, f of x equals x to the 9th power plus 1 divided by x. And once again, for the third time, you can check, put g into f to evaluate f compose g, and you will get function p of x. Well, this next one is a little bit challenging, this example, but it is so fantastic to think about, and I think it's quite fun. Here, we are given the composition of 3 functions, and we're given 2 of them. So f compose g, compose h is this. It's 12 minus x squared to the minus 2 power. And then we're told the most inside function, which is h, is 12 minus x squared. We're told the sort of most outside function is 1 over x. And the question is, what must g be? You notice if I just took f compose h, I would have this, which is almost correct. The only thing I'm missing is a power of 2 in the denominator, because this is 1 over 12 minus x squared, quantity squared. And so that gives me some idea about what to take g. I will take g of x is x squared. And then let's check. This is where I actually do want to go through the steps of checking, because I need to compose 3 functions. If we take g of h of x, this is 12 minus x squared, right? Certainly we can do this. We put in h of x. Everywhere we see an x in g of x. Now take f, compose g, compose h of x. This is just f of 12 minus x squared, quantity squared. And this is 1 over 12 minus x squared, quantity squared. But the negative 2 power and putting a positive 2 power in the denominator, this is the same thing. And so this checks. This function and this function are equal. And so my g of x works. So this is my answer. The last problem actually comes from our book, and it's super cool. We will see some wonderful things, and I will make a comment about it. So I want to work this, but understand I have both curves graphed. So in particular, let me label the blue graph is g of x, and the green graph is f of x. Okay. So what I want to do is compose in each direction, and we're going to see something fantastic. And I'm going to go back and refer to the picture. Well, f compose g, I'll do this one first, of x. This would be f of, well, g of x is the cube root of x minus 1. Now, everywhere we see an x and f, we put in the cube root of x minus 1. We get the cube root of x minus 1 cubed plus 1. When we cube a cube root, note what we get. This is x minus 1 and then plus 1. So we have x. So this is the first part of this answer. Now let's compose in the other direction. G compose f of x. This would be g of, well, x cubed plus 1. Now, what this says is everywhere in function g, where we see an x, we put in x cubed plus 1. So we will have x cubed plus 1 minus 1, and then we take a cube root. This is the cube root of x cubed, which, once again, this is just x. You notice when I compose in each direction, I just get what's called the identity function, which is, say, h of x is x. You see, we have this in each direction. And this is really saying something beautiful about these functions. It's what's called inverse functions, which you will spend a lot of time discussing, I would say in Calculus 1. But the cool thing about this type of function is if you go from one graph to the graph of its inverse, what you do is you flip it along the line y equals x. And you can see this here. Here's the graph of f. Here's the line y equals x. And if you flip the graph along the line y equals x, we have function g. So I thought that was a super cool last example to do in this lesson where we're talking about function composition. You can work the exercises for this lesson before you move into lesson 1.4.